Good day, everyone. Today, me and my group would like to discuss CombSort with my group mates JC Kataal, who will explain what CombSort is all about, and Jules Fernandez, who will go through the step-by-step process of the algorithm, and Nania Lucarini, who will further explain by showing you how this algorithm works with real-life objects, then me, Luis Fuego, who will show and explain the implementation of this algorithm in Java, and James Camania, who will show the time and space complexity of this algorithm. And finally, Angela Acevedo, who will show you how this compares to other algorithms. Without further ado, I would like to pass the mic to Miss JC over here. JC?
Let's start with explaining what is CombSort. CombSort is a comparison-based sorting algorithm that was developed as an improvement of the bubble sort. Its basic idea is to eliminate or reduce the amount of turtle-like movement of small elements towards the end of the array, which is a common issue with the bubble sort. As you can see from the GIF on the side, it shows a visual example on how the CombSort works. That will be further explained into the video. More things to note about the CombSort. In a worst case scenario, the CombSort has a time complexity of O(n) squared, but despite this, its performance can still be significantly better than the bubble sort because it eliminates small values quickly through the gap reduction step. Compared to simple algorithms like bubble sort and insertion sort, it can be more efficient for some datasets. However, it is generally less efficient than more advanced sorting algorithms like quicksort or merge sort for larger datasets. ComSort is a useful and easy to understand option for small to moderately sized arrays where simplicity is more important than absolute sorting speed. Here are the 5 steps of ComSort. There's the gap calculation, the comparisons and swaps, gap reduction, and then we will repeat the steps 2 and 3, which is comparisons and swaps and gap reduction, until we get to the final pass. These 5 steps will be further explained by my groupmate Jewel.
Here's a step-by-step visualization of a comb sort. This will be our example array, and usually the gap would equal the array length. However, if you can see the positions of the elements, there will be no elements that have a gap of 8. So no elements can be compared, which means we reduce it before entering our first iteration by dividing it with 1.3. This gives us the gap of 6. The next phase is called the comparison and swap, where you compare two elements with the distance of the gap. Swap if the one with the lesser index has a greater value. So again, these are the positions of the elements, and this is our gap. So we compare the elements, the first and the seventh element, because they are separated by a gap of 6. The values are 3 and 1. And since 3 is greater than 1 and 3 has a lesser index, we swap these values. After swapping the values, we check again if the elements with a gap of 6, which are the elements of the second element and the eighth element, which have a value of 4 and 2. And once again, 4 is greater than 2, so we swap. Since there are no other elements with a gap of 6, we move on to the phase of gap reduction. The gap is reduced by a constant factor, most commonly being 1.3. So 6 divided by 1.3 gives us a gap of 5 if you round it up. And this will end our first iteration. As you can see, the advantage of a comb sort is that 2 and 4 was already swapped in the first iteration. In the bubble sort, that will be later. The second iteration, again, comparison and swap. But this time, elements with a gap of 5. You compare the first and the sixth element as they are separated by a gap of 5. And since it's less than 6, no swaps will be made. Next element, 2 is less than 3, no swaps will be made. Then 7 is greater than 4, so there will be a swap of elements. We swap the values at the third and the eighth element, which are 4 and 7. Then we move on again to gap reduction. These two steps are just repeated through the iterations until your gap equals 1, which means the array is sorted. We reduce 5 divided by 3, then it will be now 4. Move on again to our this is the final phase, the final array in our second iteration. So we move into our third iteration. We compare uh, objects with a gap of 4. So 1 is less than 5. No swaps will be made. 2 is less than 6. No swaps. 4 is greater than 3 and 4 is a lesser index. So we swap the values of the third and seventh element. After this, we check for the fourth and eighth element. Since 8 has a lesser index than 7 and 8 is greater than 7, we once again swap the values in these places. So move on to the final phase of our third iteration. The gap is reduced by a constant factor. 4 divided by 1.3 will be 3, and that ends our third iteration. As you can see, most values are in place. The only ones that are out of place are uh, the last half of our array. So with a gap of 3, we start our fourth iteration. Once again, comparison and swap. We compare 1 and 7. 1 is lesser, so no swaps. 2 is lesser than 5, no swaps. 3 is lesser than 6, no swaps. 7 is greater than 4. So once again, we swap the elements and we move on to 5 and 8. Since 5 is less than 8, there will be no swaps. And as you have noticed, we move on to gap reduction, but at this point, it is unnecessary since the array is already solved. The comb sort will go until your gap equals 1, which means that it goes through, compares every element that are next to each other, and that means that the elements are sorted. So with the gap in fourth iteration, the elements are already sorted, but since the comb sort goes until your gap equals 1, then I will not show you the process of that since no swaps will be made. It's already sorted. So this is our fifth iteration. The gap equals 1 and our elements are sorted. That is all.
This is a visual representation of the CombSort process using rectangles with different sizes. We will be sorting these by length in ascending order or from shortest to longest. Compared to the bubble sort, which compares objects that are adjacent to each other, the CombSort introduces the gap denoted by these arrows, which allows us to compare objects that are further apart from each other. The initial gap value is the amount of objects that we have to be sorted. Since we have 1, 2, 3, 4, 5, 6, 7 rectangles, the initial gap value will be set at 7. Now, we will be comparing the objects at the gap value, then moving the arrows to the right. So we can begin the first step. G is longer than A, therefore we have a swap. Move the arrows to the right. Since there's no more objects, the first pass is complete. Now, we need to find the new gap value, which is determined by dividing the current gap value, 7, by 1.3, which is 5. So our new gap value is 5. 1, 2, 3, 4, 5. Let's start again. A is shorter than D, no swap. E is shorter than G, no swap. Now we need to find the new gap value again. So 5 divided by 1.3 equals 3. 1, 2, 3. Let's begin again. A is shorter than F, no swap. E is longer than B, so we have a swap. Move the arrows to the right. C is shorter than D, no swap. F is shorter than G, no swap. So let's begin again. Let's divide the current gap value by 1.3. So 3 divided by 1.3 equals 2. 1, 2. Let's start again. A is shorter than C, no swap. B is shorter than F, no swap. C is shorter than E, no swap. F is longer than D. Yes, we have a swap. Move the arrows to the right. E is shorter than G, no swap. And now we have completed the sorting process. The rectangles are sorted from shortest to longest.
Alright, before we start looking at what the implementation of this code would look like in Java, let us first take a look at this algorithm pseudocode. If you recall Joule and Enia's explanation of this sorting algorithm, we first start with getting the initial gap value, which is equal to the size of the array, and assigning the gap shrink factor, which is 1.3, and the Boolean variable sorted to true, which will be used to check if the array is sorted or not. We then move on to the meat of the algorithm here, which is this while loop statement that continues until the Boolean sorted is true. The first statement in this loop is to divide the initial gap value by the shrink value, which is usually 1.3, and is being used in this pseudocode. After which, it checks if the gap value is less than or equal to 1. The purpose of this if statement here would be to check if the data is sorted or not. If it's sorted, then the loop ends after this iteration, and if not, it continues. And then we move on to the second while loop statement of this code. We first initialize a variable I, which is used to traverse the array to 0, which will then be used for the while loop statement that continues as long as the sum of I plus the gap value is less than the size of the array. Inside the loop, there's an if statement that checks whether the value at the current index is greater than the index at the sum of I and gap. If this condition is fulfilled, it swaps both values and sets the Boolean sorted value to false, and the if statement ends there. Afterwards, I is incremented, and this completes the first pass. This entire thing loops over and over again until the sorted value will equal to true, in which case it will do one more comb over the array to check if there's still a value that hasn't been sorted. Afterwards, it will do a swap which sets the sorted value to false and does the loop all over again if it's found a value that hasn't been sorted. It does this all over again until the if statement in the second while loop never happens, which means that the array is finally sorted. Now this is what the Java code implementation would look like. There are other ways to implement this algorithm. This is just one of many ways. As you can see, it first initializes the gap value equal to the size of the array. It then initializes the Boolean swap value to true. After which, a while loop is created with the conditions being that the gap is not equal to 1 or if swap is equal to true. It then calls a method which divides the gap value by 1.3, after which it sets the swap value to false and moves on to the for loop statement of this code, which is equivalent to the second while loop shown in the pseudocode earlier. The purpose of this loop is, like earlier, is to traverse the array and checks if the index at this position is lower than the index at that position, which then swaps both values with each other and sets the Boolean swap value to true, which then completes the first pass. Similar to the pseudocode shown earlier, this loop continues until the condition for the for loop is not met, and it ends the loop there with the data being sorted. That is all for my explanation. I would like to leave it to James to explain the time-space complexity of this algorithm. James?
The CombSort is a relatively simple sorting algorithm that improves the bubble sort. It gets its name from the way it reduces the gap between elements being compared and swapped during each pass. The time and space complexity of this sorting algorithm are as follows. In the worst case scenario, CombSort has a time complexity of O(n squared, where n is the number of elements to be sorted. This worst case time complexity occurs when the initial gap between elements are relatively large, or the algorithm needs to perform many passes. It has an average case scenario of O(n squared divided by 2 to the power of p, where p is the number of increments. CombSort generally performs better than the worst case time complexity, but is still considered less efficient than some other sorting algorithms with better average cases. The best case times complexity of the CombSort is O(n log n. This best case scenario occurs when the input data is already nearly sorted and the algorithm doesn't need to perform many swaps and passes. The space complexity of the CombSort is O(1), which means that it is an in-place sorting algorithm and it does not need additional memory allocation that goes with the size of the input array. However, it uses a constant amount of extra memory for variables and temporary storage.
For now, we will have the efficiency of CombSort compared to other sorting algorithms. in terms of space complexity, time complexity, and practical performance. First, for time complexity, it has a best time complexity of ON, which outperforms some other quadratic sorting algorithms, such as bubble sort. And this happens when the input data is already mostly sorted. However, the worst time complexity of CombSort is ON squared, which occurs when the input data is in reverse order. This makes it less efficient than many other sorting algorithms like quicksort, merge sort, and heap sort, which have average and worst case time complexities of O and log n. Next, for space complexity, it has a space complexity of O1, meaning it sorts the data in place without requiring additional memory allocation for data structures like arrays or linked lists. And this is advantageous when memory usage is a concern. However, some disadvantages or drawbacks is that it still incurs some space overhead for variables and may not fully optimize cache usage. Additionally, its simplicity and in-place nature makes it less suitable for certain scenarios, such as sorting extremely large datasets or optimizing cache performance. Next, for practical performance, it is however not wide. CombSort is however not widely used in practice for sorting large datasets due to its worst case time complexity, and it can result in slow performance for such inputs. However, it may be more suitable for small to medium-sized datasets where simplicity and low memory usage are more important factors than sorting speed. Overall, there are better sorting algorithms available, such as merge sort or quick sort, or even some of the built-in sorting functions provided by some programming languages, which are optimized for performance and handle a wide range of input types efficiently.